So, hi everyone, welcome to Ground Visual Computing Seminar. Today we are delighted to have Nick Sharp as our guest speaker. Nick is a skilled researcher with a background in geometry processing, computer graphics, vision, and 3D machine learning. His work centers around creating new algorithms and representations to enhance the efficiency, reliability, and accessibility of computing with geometric data. Currently, he's a senior research scientist at NVIDIA. Just a quick background, Nick completed his PhD at CMU, where he was advised by Ken Crane. Following his doctoral studies, he did a postdoc at the University of Toronto, working with Alec Jacobson. Moreover, Nick's expertise in the field has been recognized with several awards, including the Best Paper Award at SIGGRAPH 22, Best Student Paper at SGP 20, as well as the Software Award at SGP 22 for Polyscope. I'm guessing some people here must have used it. We are really fortunate to have Nick here today to share his knowledge and insights on the computational geometry of neural implicit surfaces. Please join me in extending a warm welcome to Nick.
All right, Nick. Thank you so much for the introduction, and thank you so much for organizing and for having me here. Really excited to chat with everybody, both now and hopefully some afterwards. I'm happy for people to ask questions or anything during this, although I probably can't follow along with the chat or anything. So if there are any questions in chat, just call them to my attention and we can sort it out. Yeah, so let's get going. Oh, there we go. Cool. So I'm here to talk today a little bit about two different flavors of research in geometry processing and 3D visual computing, which is sort of where two of my favorite topics meet each other. And the first of these topics are low-level building block geometric algorithms. So these are not, the exciting end task that you work on. These are the tools that get you there. And this is what a lot of my research is actually about, is not on any one particular end task, but on providing people new building blocks that enable you to do sort of all kinds of exciting things in downstream applications in graphics and in vision and in machine learning. And the other side of this is really just machine learning with 3D geometry. And this is exciting because in terms of building blocks, it's kind of wide open. We have a bunch of new tools and we have a bunch of new applications that have really come into the limelight in the last few years in terms of how do we do learning on 3D geometry. And we're still kind of figuring out what the right building blocks are for these kinds of applications. And in my opinion, 3D machine learning and sort of the intersection of these applications of neural networks with visual computing is really, really exciting right now. And one reason for that is that we're kind of living in the golden age of doing data-driven 3D geometry and visual computing right now for a couple different reasons. One big reason for this is that 3D data has just kind of started to become widely available for the first time. Like, although we had fairly large and interesting image data sets going back, 15, 20 years now, the widespread availability of 3D data, or even just, collections of multi-view images and things like that, and the ability to actually work with data-driven techniques in 3D has really blown up over the past 5 years or so. And in my opinion, this has kind of sent shockwaves through geometry processing and people like me who like to build these lower level building blocks, because it's forced us to transition from manual to automatic techniques for manipulating 3D data. And what I mean by this is that if we look at the kind of algorithms we use to say, manipulate a 3D triangle mesh, a lot of these algorithms were invented in, the 90s under the perspective that there would be a skilled human sitting there driving the algorithms, right? These are algorithms that were meant to be run when you click a button, when you set a knob, when you select some elements and do some operation with a reasonable choice of a parameter. So these algorithms were sort of envisioned as tools for a skilled human to use. And then what we started doing around 2014 or so was we took those algorithms and we started running them en masse on millions and millions of meshes automatically in computers without ever looking at what's going on, and even doing crazier things like differentiating through the application of these algorithms with respect to the input in order to train some neural network or something like that. And when we did this, it turned out that a lot of the algorithms that we thought we were happy with, actually aren't so great when we apply them in this automatic way on large pipelines of crazy data and in differentiable settings and things like that. So what's been going on in the past 5 years or so is that we've been revisiting a lot of these classic building blocks to figure out what really works and what really is well suited for this future of automatic geometry processing. Now, the thing that makes 3D hard and 3D interesting, and is probably familiar to a lot of the people listening here, is that in 3D, we have a lot of different representations. If you're working with image data, there's kind of one obvious way to represent an image as a grid of pixels, and 98% of the time, that's the representation you want to use for images. In 3D, things are very different. If I want to represent some 3D shape, it could be a surface as a point cloud. It could be, a binary voxel grid. It could be a tetrahedral mesh where I've decomposed the space into tets. It could be a triangle surface mesh that we use most often for rendering and graphics. Or there's even more. We have splines and subdivision surfaces, hierarchical CSG and part-based representations, implicit surfaces, and many, many more. And this is kind of what makes 3D fun, is because no one of these representations is always the best one. In different situations and for different problems, we want to choose a different representation that has different trade-offs. And in particular today, I'm going to talk a bit about these implicit surface representations, which have become a lot more interesting in the last few years with the advent of implicit neural networks, and what some of these classic geometry building block questions look like in the context of implicit surfaces. So the outline here is that first I'm going to talk a little bit more high level about why we do geometry on neural implicit representations. What does that mean? Why is it interesting? And then do a little bit of a deeper dive on a technique called range analysis that we found was really effective for doing some quite useful geometric queries on this kind of data and enabling some of these downstream higher level operations and applications. So some of this will probably be very review to some of the people listening, but I want to get us all at the same page to begin with. So the basic idea of neural implicit surfaces is to represent some 3D shape as the level set of a function. So very generally, you'd say you imagine have some function that maps our three spatial coordinates, x, y, z, to a scalar value. And then we'll say that, the surface that we're interested is just the set of points where that function evaluates to 0. And generally, by convention, we'd say the places where the function is negative are inside the object, and the places where the function is positive are outside the object. And these kind of implicit surfaces go way, way back to the 70s and 80s, where we'd use different analytic representations of this function f, or maybe tree-like or sort of program representations of these functions. But what's become interesting recently is to think about neural implicit surfaces, where this function f is a multi-layer perceptron. And then we fit the weights of this MLP in order to encode some shape that we're interested in. And there's an important difference here from what your mind goes to first when we talk about machine learning, is that usually in machine learning, you're imagining I have a giant data set of many, many examples. I have thousands of shapes or something like that, and I'm training a neural network to somehow represent something about all of them. But here we're doing something very different. We're really just using the neural network, at least in the basic case, as a set of basis functions, or not really basis functions, but as a function space to represent our implicit surface. And we're fitting one neural network to represent one shape. So I don't actually like this abuse of terminology, but we're overfitting the neural network to represent one shape that we care about. You can imagine trying to do this in ways that build in priors or that generalize across many shapes, but we're not really going to talk about that today. So this is basically all that I'm going to say about training neural networks, about data sets, about all of that. Here, we're just using our neural networks as a one-off function space to represent a single shape that we're interested in. And this was, to me, a surprisingly effective and exciting thing to do. So this example on the left was, I think, the first one that really got me excited about this representation after I'd heard about it from other folks in the literature. So here's a shape where I took a rib cage and I trained a really small multi-layer perceptron that's just 7,000 floating point weights to represent the level set of this shape. And you get an amazingly accurate, smooth, sort of beautiful looking encoding of this shape with just 7,000 floats. And even better, you can start pushing this farther and adding in, say, latent parameters. So here, rather than just having XYZ inputs to the network, we add one more input. So it's XYZT, and the time parameter now encodes an animation. So I have the classic dancing horse model here, galloping horse model. And we just fit the neural network to many sort of frames of this animation through time. And this is just an example of how this representation is exciting, because it's really, really easy to play games like this. And this is part of sort of a larger research movement going on right now that a lot of people are calling neural fields. And I think there's actually some really cool work from some folks who may be here today on neural fields and sort of bringing this all together. You might have heard of things like NeRFs, which are a neural field version where instead of an inside-outside function, we work with a density. And then there's lots of other exciting examples of sort of representing data in space via these neural networks that are overfit to coordinates. But this is really exciting in the surface geometry case because, well, traditionally we have all of these different representations that we might use to represent 3D data, and a whole bunch of other sort of fitting or optimization tasks that we might want to do with them. Things like reconstructing data or compressing it or doing inverse design tasks to fit some desired representation to some design constraints. And what ends up happening is that each of these representations forces a different algorithm for the task, and the sort of cross product of the Cartesian product of all of these means you end up with a lot of complex techniques to fit each of these representations to each of these tasks. And what's really neat is that when we work with these neural implicit representations, basically every task just ends up being gradient descent on the weights of the neural implicit representation. And this kind of makes it plug and play with lots of different downstream tasks we might want to do. So this means that basically, even if you wanted to say combine these things together, you wanted to do 3D reconstruction with an inverse design objective, well, you just add the two loss functions together and optimize them both. That's really powerful and really exciting. You also get things like adaptive complexity for free. So here's an example. I'm going to say more about this later, about this particular example I'm showing here, but I'm just using it as a little talking point here. So this is a simple inverse rendering problem where I'm optimizing a shape to match 20 synthetic camera views of the shape. And if I was going to do this with a triangle mesh, there's a lot of hard things I'd have to do. I'd have to think about remeshing. I'd have to think about subdividing and allocating complexity of my triangle mesh to represent the shape. But if my underlying geometric representation is just an implicit surface, then all I need to do is gradient descent on the weights of the network, and I don't have to worry about where I'm allocating the geometric complexity. And even beyond that, it's easier to sort of plug and play all of this with the larger machine learning toolbox. So these are all reasons why these neural implicit representations have become extremely popular in vision and graphics over the past 3 or 4 years. There are some downsides, though, and two really big ones that stand out to me. One is that it can be very computationally inefficient. So as an example, if I wanted to just render a picture of a surface encoded as one of these neural implicit representations versus a triangle mesh, we're probably using 2 to 3 orders of magnitude more computation to do so. And also, it can be hard to do operations on these representations because they are implicit rather than explicit. And that's going to be the focus of what we're talking about today. So to make this concrete, suppose I am using these neural implicit shape representations, right? I have some shapes that I care about for my applications. I've encoded them as implicit neural networks. How do I do queries on those shapes? The one we do most often in graphics is just casting a ray, right? I have a camera and a pixel in that camera, and I want to know if I see the surface in that pixel, so I want to cast a ray from that pixel and test whether or not it intersects the shape. How do you do that? Or maybe more interesting, suppose I have 2 of these shapes, both encoded as neural implicit surfaces, and I want to know whether or not they intersect each other. Do 2 neural implicit surfaces overlap in space? This is a really basic operation to want to do if you're doing robotic path planning or physics simulation or something like that. If I have triangle meshes, it's really easy. If I have implicit surfaces, it's not obvious at all to figure out whether or not 2 of these surfaces intersect. So the classic answer to this, and one you might have heard of if you've worked in this space, is something called sign distance functions. So to recap here quickly, a sign distance function is when we have one of these implicit surface representations, but our implicit function not just has the property that it's inside-outsideness defines the shape, but furthermore that the magnitude of the function gives the distance to the surface. Or it's actually okay if it just gives a lower bound on the distance to the surface. And a different sort of analysis way of saying that is that we have some known Lipschitz bound on our implicit function. And if you have one of these sign distance functions, then they're great for doing all kinds of geometric queries. The classic example is casting rays using an algorithm called sphere marching, where we use this sign distance function bound to step a ray forward. So here's my implicit shape again. This little black arrow and dot is a ray that I want to cast. So what we do is we look at the magnitude of our implicit function at the center point of the ray. the magnitude of the function tells us a sphere that must be empty, that must not contain the surface. So then we march forward to where that sphere intersects the ray. We sample the value of the implicit function again. We look at its magnitude. It tells us a sphere that must be empty. So we step forward again, and we continue this process, sampling the magnitude of the function, stepping forward, forward, and forward, until eventually our ray converges to a point on the surface. This is great. This is a classic algorithm, but it only works if you have a signed distance function. So if we had a signed distance function, it would be great. But implicit signed distance functions in this neural context have a lot of downsides. One big one is that when working with neural networks, we have no way of forcing them to definitely encode a signed distance function. All we can do is write down a loss function that says, hopefully, probably try to encode a signed distance function, which means that in some places it doesn't encode a signed distance function, and then you have robustness issues on your downstream queries and operations where this property doesn't hold. Maybe more fundamentally, even in the best case, if you try to fit a network to be a signed distance function, it's only a signed distance function at the end of training, or sort of once training has succeeded. So this means if you want to apply these kind of geometric queries to define your loss functions, you can't, because the property definitely doesn't hold at the beginning of training when you want to apply your losses early in training. And also sometimes we just want to work with surface representations that aren't signed distance functions. For instance, these like log sigmoid representations on occupancy functions have a lot of benefits and have relationships with density fields that are used in NeRFs and things like that. And it would be great to be able to do geometric operations on these without having to worry about them, whether or not they're sort of precisely encoding signed distance function. So all of this is to say, we want to use these neural implicit functions to represent shapes because they're great for all kinds of operations and applications in computer graphics and vision, but we have no way of doing queries on them. So how can we do operations like geometric queries or building hierarchies on these neural implicit surfaces without making any assumptions about it being a signed distance function? So this is the problem that I'm going to share one particular solution for you with. And interestingly here, usually when we talk about neural networks, we define a new architecture or a new training procedure or something like that. We're not going to do any of that today. Instead, I'm going to describe a set of techniques for analyzing neural implicit representations that you might already have. So the setting here is you're for some application or some other technique, you're fitting these kind of neural implicit surfaces. We're going to give you a new toolbox to analyze them. Yeah, are there any questions so far on what I said as I transition in here?
It's kind of a, I don't know, super hypothetical, far out there question, but about the issue of, the best we can do is try to encourage our neural networks to fit an SDF. Whether that's like by directly regressing SDF values, or even if you're training on some other objective like classifying inside outside, you could have some regularizer that says, sample a bunch of points, try to make sure it satisfies the iconal equation, all that stuff. Do you think it's possible to design a neural network architecture, and by that I mean like function space, where everything is an SDF by construction? Like, is that a thing that we could do potentially?
Yeah, I love this question. This question was actually what I started working on when we wrote this paper, because I tried to do it for 2 months and then gave up and decided we had to try something else.
Yeah.
Yeah, I think this is super interesting. I think people are working on this, and I hope that someone succeeds. One challenge on it is that even like the most natural thing to do is to, as you say, try to satisfy the iconal equation everywhere, which says that the gradient of your function is exactly 1.
Yeah.
The hard thing is that even this is not enough. Even if you give me a function that almost everywhere satisfies the iconal equation, it's still not guaranteed to be an SDF, because you can have sort of wiggle, right? You can imagine if you're walking away from the surface, it could be increasing, and then it could flip and start decreasing. And still satisfy the iconal equation almost everywhere, but not be an SDF. So people in PDEs, they call this like a viscosity solution, I think is the keyword to look for. So really, you don't just want to satisfy the iconal constraint, you want a viscosity solution to the iconal constraint. And that's the part that really makes it tricky, and the thing that I've always sort of gotten hung up on.
Cool.
So yeah, I don't know. I love this question. I hope someone can solve it. If you have ideas, I'm all ears. Great. Okay, so how, if we don't know anything special about our neural network, I've handed you a random neural network that might even just be randomly initialized. how can I do geometric queries against the level set encoded by that neural network? This sounds pretty impossible, but to get there, we're going to resurrect a tool that goes way back to the 1960s and a little bit even before that, called range analysis, which is a really, really interesting numerical method that's just a general cool tool to know. So the basic idea of range analysis is to bound the output of a function of interest over a range of inputs. And I think it's easiest to understand range analysis by just walking through the simplest kind of range analysis, which is something called interval arithmetic. So the basic idea of interval arithmetic is to say, imagine I have some function that I'm evaluating or some computational graph, and I'll take every scalar that appears in that computation and instead split it into upper and lower bounds on that scalar and push these bounds forward through the computational graph. So what we'll do is we'll start out at the beginning of our functions. This is kind of like a program transformation. At the beginning of our function, we'll have some bound of a range of inputs that we're interested in. And then we're going to use update rules to push these bounds forward through a computational graph until we eventually get out bounds on the output of the function. So to give an example, if we just wanted to add a constant, then that would be just adding a constant to the upper and lower bounds. If I wanted to multiply times a constant, then here's the update rule. It ends up being a min or a max, or if you know the sign of the constant you're multiplying by. Or here's the update rule for multiplying two bounded functions together. Pardon me. And then for nonlinear functions also, it's easy for monotonic functions, but we can write down these update rules. So the point here is that we're saying we have a computational graph. It could be a bunch of multiplications, additions, nonlinear functions. We track a bound, an upper and lower bound for every scalar variable, and we push these upper and lower bounds forward through the computational graph until we eventually get out bounds on the output. You can think of this as being kind of like forward mode auto differentiation. Sorry, was there a question there?
No, I think it was just somebody who wasn't muted said
Gotcha.
something.
Yeah, so this is kind of like forward mode auto diff. So forward mode auto diff says I want to compute derivative, so I'm going to track some extra data for each value and push it forward according to rules. Here we're doing the same thing, except instead of computing derivatives, we're computing bounds on the function. And you can start to see how this is exciting, because if I do this range analysis and it tells me that a function, our implicit function, is strictly positive or strictly negative in some region, then I can start using that as a foothold to do geometric queries. Two things that are going to be important about this, though. This procedure is guaranteed to always give valid bounds. So if you do interval arithmetic on your computation graph and it gives you upper and lower bounds, those upper and lower bounds are always really true bounds on the output of the function. It never exceeds those bounds in the region you just analyzed. However, they may not be tight bounds. And in fact, they may be significantly looser than the actual set of values that that function takes on the range, which is going to be important later. Also, there's a really cool pointer here that the one other place that this has showed up in machine learning is in robustness ML. And some of these people who do like trustworthy neural networks have done some really cool work showing how range analysis can be used for that. But otherwise, it hasn't been really used on the visual computing side of implicit neural representations before. Which is funny because it's sort of a known trick in the graphics and games community. For instance, this was used a lot in some of these really cool implicit shader toys, these like Inigo Quiles examples you might have seen, or on this game Dreams for the PlayStation that uses a lot of really cool techniques. They extensively make use of range analysis for analytical functions. So it kind of seems promising to do it for neural implicit functions too. So let's come back to this raycasting example. Supposing I have this shape on the right represented as a neural network, and now we don't know anything about it. It's not necessarily an SDF or anything like that. But instead of sphere marching, we can use interval marching to push this ray forward. So let's imagine we take some bound at an arbitrary initial size, and we do this interval range analysis along the ray. And the range analysis tells us that the function is bounded away from 0 on that along that region of interest. Then great, we can step forward. Now suppose we try analyzing this next region. Well, remember I said that sometimes the bounds aren't tight. So let's suppose we got unlucky here and our bounds covered 0, even though this region actually was outside of the shape. That's okay, we can just try a region of half the size. There we go, it was bounded away from 0, and we keep stepping forward until eventually our ray intersects the surface. This range analysis does have the property that as you make the intervals smaller and smaller, the bounds eventually become tighter and tighter, and that's enough to guarantee that this procedure converges and eventually your ray hits the surface. So this is awesome. We can do raycasting, be guaranteed to get the right answer, even on functions that we don't know anything about. However, in practice, there's a really big problem here, which is this issue of loose bounds and cancellation. So these bounds from interval arithmetic are always accurate, but they may not be tight. And the main thing that goes wrong is cancellation inside of your computation graph. So to walk through a simple example here, consider the function where our input is x and our output is 2x minus 1. And you may notice that this is just the identity function, but I've written it in a funny way. So suppose we do interval analysis on this really simple function, and we start out with the interval 0 to 1 that we care about. Well, if we push these bounds forward, according to the rules I showed before, the actual output should be that the range of this function is from 0 to 1, because it's just the identity function. Its value over the range 0 to 1 is 0 to 1. However, when I push forward these bounds, what happens is that I get 2 times the interval range 0 to 1 minus the interval range 0 to 1. This becomes the interval range 0 to 2 plus the interval range -1 to 0 by just pulling the multiplications inside. And then when I add those two together, you get the interval range -1 to +2. So interval arithmetic delivered on its promise. This is an accurate, a valid set of bounds on the output of the function. But even in this really simple example, they're not tight bounds. They've become loose because 2 numbers canceled out inside of the computation graph. This turns out to be a huge problem if you try to apply interval arithmetic to neural networks, because inside of a linear layer of a neural network, there's a huge amount of cancellation going on. So when this happens, you get astronomical bounds. In fact, when we first tried applying this to neural networks, we would get out bounds like -1 million to +1 million on the output of the neural network. So, technically this is a correct bound, but it's not at all useful for doing geometric queries. So the solution here is a slightly more obscure variant of range analysis called affine arithmetic. And affine arithmetic is a little bit complicated to dive all the way into in a presentation here, but I can give the high-level idea. You should think about it as if interval arithmetic is like the 0th order expansion of interval analysis, then affine arithmetic is like a 1st order expansion. So you're not just concerned with the values of the functions, you're concerned with the slopes of the functions and putting bounds on those. And much like we see with something like a Taylor expansion, going from the 0th order to the 1st order gives you a huge increase in accuracy. The way affine arithmetic works is that rather than just tracking upper and lower bounds for each scalar function, we're going to track a variable length expansion of coefficients. So we're going to have each scalar in our computational graph will become a length n expansion of coefficients. So these are these x0 to xn that I've written here. And the way we interpret them is that the value of that function, the value that the scalar x takes is given by the constant, the first term x0, plus a summation over a logical coefficient or a random coefficient, as they say, epsilon I, which ranges from -1 to +1. So this seems like a weird thing to do, but it's going to turn out to be really, really effective, because what happens is that when you add these affine quantities together, they can cancel out. We let each of these epsilon coefficients correspond to a distinct set of variation. So what this means is that when I go to add two scalar quantities together that are tracked by affine arithmetic, when this cancellation happens, we can actually just let the coefficients cancel. Then every time we do a nonlinear operation, what we do is we just add one more of these epsilon coefficients and get one more term in our expansion. So this is a little bit weird. This means that as we're evaluating our neural networks, every time we hit one of the nonlinear functions in our neural networks, we pick up a bunch more terms in this affine arithmetic expansion. And if you did totally naive affine arithmetic, by the time you got to the end of evaluating the computational graph of a neural network, you would have something like 800, 1,000 order terms on the expansion for each scalar value in your neural network's computational graph, which is insane. Fortunately, what you can do is you can truncate this expansion and keep only the most significant terms and pick up a small but still bounded amount of error. So a lot of the sort of low-level technical work we had to do here was figure out just the right way to implement affine arithmetic and truncate this expansion to allow us to implement it efficiently on neural networks and get out these bounds. But in the end, it works great because it's exact under affine operations. So we don't lose any tightness in the bounds on our representation when we evaluate an affine layer in a neural network. And this means that we're doing a bit more compute, but we now get out actually meaningfully tight bounds when we go to analyze ranges of values pushed through a neural implicit function. To give a rough idea here, I think in our implementation, doing an affine arithmetic evaluation of a neural network is about 10x more expensive than a normal forward pass. So there is some cost associated with this, but it's not totally astronomical or anything like that. So the sort of high level takeaway. Oh yeah, I hope you can see it and it's not clipped off by the screen sharing here. But at the bottom there's a textbook citation, which is the place I recommend checking out if you're interested in more of this. So the sort of takeaway of range analysis is that it's like autodiff, but it lets you compute bounds rather than computing derivatives. These bounds are always valid, but they're not necessarily tight. But we showed how you can use affine arithmetic to get tighter versions of these bounds, even on neural networks where you have lots of cancellation happening in the affine layers. And this is great because this is a sort of classic secret sauce in numerical methods that we can now apply to this neural case and to help us do queries on implicit neural representations. We can derive expressions to push forward this computational graph for all kinds of different functions that might arise. Although there are some tricky problems to deal with here, in particular that the bounds of the function depend on how your expression is written algebraically, like we saw with that identity example, which is really weird and not what you think of when you think of autodiff or automatic program transformations. And also just a software concern that this is not a widely implemented technique. You know, PyTorch will do autodiff for you, but it will not do range analysis for you out of the box. So there's some engineering to do here. So in our case, we condense this down to a single function, which I'll call here is this range bound function, which says, given some function f here, which happens to be an implicit neural network, and a query box that we're interested in analyzing. So this could be either a 1D interval like a long array, or it could be a 3D box, which encodes some 3D region in space or any other dimension. Then we apply this range analysis, we push these affine bounds forward through the evaluation of our neural network, and we get out that our function is either strictly positive over that range, strictly negative over that range, or maybe not necessarily either over that range, which could be because our function actually spans 0 on that range, or just because the bounds weren't tight enough to say for sure. We use some tricks to implement this in a way that runs quick on GPUs. And if anyone wants to talk more, I have some interesting, there are some interesting things that show up here from the sort of programming languages, program transformation, system design side that turned out to be a bit more challenging than we might have hoped. But the end result is that you have the ability to analyze these neural networks, get out these range bounds, and start building up higher level geometric queries and applications. And that'll be the next section where we see how we can put this to work or use analyzing these implicit neural networks for tasks in visual computing. Does anyone have any questions about the range analysis stuff here before we go on? Cool.
I think
go ahead.
I was just curious why the range analysis is both sided. Like if the ray is going forward, but the box you analyze is kind of symmetric about the point. Is there like a reason to do that kind of a box rather than just forward moving?
Oh, I see what you're saying. Yeah, so in that case, we would just analyze the forward place. So the way I just defined this procedure, it's centered around a box. But there, if we wanted to analyze some chunk along the ray, I would just put this center in the middle of that chunk where so that the tail of the range starts at the current marching point along the ray and then push it forward like that.
Makes sense. Thanks.
Yeah, it's a good question. It would be nice if you could do like one-sided open analysis. So to like analyze a region from 0 to infinity or something like that. But we never came up with a way to make that work. So it wouldn't surprise me if you could do it with other versions of range analysis, and that'd be really useful, especially in this ray casting setting. Cool. So this ray casting is, again, the most basic and common example. By the way, these blue figures that I'm showing are all just little implicit MLPs that I fitted for this purpose. They're from a variety of different data. Some of them are SDF, some of them are occupancy networks. I used a couple different activation functions. They're sort of a small zoo of random different implicit neural networks showing up on this. And all of them are fitted directly to ground truth known geometry, just as examples here. So as we said before, we can use this interval analysis to march a ray forward and find where it intersects the surface. Here's an example that shows if we do this for every pixel in an image, it shows how many steps it took. And you see the usual pattern that often comes up with ray marching and ray casting, that the occlusion boundaries right near the silhouette are where you have to take the most steps, because as the ray gets very close and almost hits the surface, you take a lot of tiny steps. By the way, this raycasting procedure is how I produce all of these blue renderings that we're seeing by just marching one ray forward per pixel. The trade-off here is that if you didn't have this kind of implicit range analysis procedure and you tried to do these renderings, the only thing you could do is take fixed size steps forward. But this is tricky because if your fixed size steps are too big, like you see on the left, then sometimes you step over the entire surface. So you get these false artifacts where you have little jagged holes in your surface because your steps were too big and you skipped the surface entirely. In the middle, if you take smaller steps, then this doesn't happen, but it becomes extremely expensive because you're taking millions and millions of tiny little steps to march forward. Whereas on the right, here we get a guarantee that our rays never miss the surface, and it ends up being faster than either case. This is still not as fast compared to like the latest and greatest fastest NERF renderers or something like that, but this is kind of a very different flavor of tool, that this is sort of a guaranteed worst case geometric primitive that works even on nonsense randomly initialized networks. It works on all kinds of different settings you might be in, which is very different from like fitting a specialized neural NERF architecture or something like that that's meant to be quickly rendered via volumetric ray casting. So the setting's a bit different here, but it's still reasonably performant. And you can start playing cool games with this where rather than casting each ray independently, you process an entire frustum or bundle of rays at once. So here's the kind of picture on the bottom. If you imagine a cluster of rays in image space, we don't need to analyze each one independently. We can stick a 3D volume over all of those rays and march the whole volume forward all at once. So this ends up being like a hierarchical renderer, and it immediately gives us a 4x speed up here that improves on larger image sizes. The thing that's really exciting about this, for me though at least, is the ability to do geometric operations beyond just ray casting. And the bread and butter technique for doing geometry beyond ray casting is building KD trees, which are a classic tool in spatial analysis. So once we have the ability to do these range queries, we can start building KD trees over space that say for each cell of the hierarchical tree in space, we know that the function is strictly positive, strictly negative, or maybe not necessarily either inside of that cell. So the algorithm is just start with a big cell in space, do range analysis on that cell to check whether the function's positive or negative there. And if it's not necessarily either, then split the region in half and recurse onto either side. So here's an example on the right. Hopefully the video is playing decently for you, where I've built one of these trees on a simple implicit function. I think the implicit function is being visualized in the middle as just a coarse marching cubes extraction. And then in the domain on the outside, I'm building this KD tree. So each cell here, each square is a cell of the KD tree, or each cube is a cell of the KD tree. The yellow cubes are the ones that get classified as being strictly positive. Inside of the shape, there are other green cells you can't see that are getting classified as strictly negative. And here I stopped building the tree partway down, so I only descended a fixed number of steps into the tree building hierarchy. So there are also these purple cells that we haven't yet classified as positive or negative. If we kept descending, they would eventually turn yellow and get classified as strictly positive or negative. The other thing that I think is cool about this visualization is that you see these sort of lines shooting off of purpleness, which are places where we had to descend more to classify the function as positive or negative. And what these actually correspond to are the elbows of the ReLUs on the first layer of the neural network. Because right around the elbow of a ReLU, you have to descend a lot more to classify the value of the function there. So they actually show up in the KD tree.
That's
Um,
interesting. The structures of these KD trees don't really look like the structures you would get if you built one over a triangle mesh because of that. Yeah.
yes, exactly. It's very different here. So it still kind of just works out of the box. It's just a cool observation that this happens if you examine the construction. Maybe there's some way to exploit this structure, although we haven't done anything special with it yet. Cool. So once you have this KD tree, then you can use it to implement all kinds of accelerations and queries and operations on geometry. One really quick note is that I said we wanted to make these queries always work, which means we have to define what we mean by correctness and convergence. And it's tempting to write down a bound based on the value of the function to say that we're going to be correct within some magnitude of the implicit function. But that's not actually a meaningful thing to do on this, because if you have, say, a randomly initialized neural network, then a very small change in the function value might put you very far from the level set. So bounds based on function value don't actually tell you anything about geometric accuracy to the level set. So instead, we define correctness here as being correct in the sense that the query gives the right answer for a surface, which is a dilation or a contraction of the true level set by some very, very small parameter delta. So here, delta, I think, is like 1e -5 of the bounding box in the examples I'm showing. If you really wanted to prove correctness here and get out your old school geometry mindset, you would prove correctness even with robustness to floating point errors. And you can do things like this with range analysis by carefully controlling rounding modes. We did not do any of this here. We just do ordinary plain old floating point with no special treatment, and everything more or less just worked fine. But this is a route you might want to go to if you wanted even stronger guarantees of accuracy. But to show some other operations here, so here's an example of sampling a surface, which shows up a lot, say, when evaluating loss functions. So we have some implicit neural representation, and we want to sample a large number of points in space near the surface, in particular ones where the magnitude of the function is bounded. Here, I'm sort of committing the sin I just mentioned a moment ago, where I said that bounds on the functions might not be what you want, but this is what people usually use in practice when they talk about sampling near the surface. So what you could do is you could just rejection sample by just randomly grabbing points in space and testing the magnitude of the function there. But what we can do instead is build this KD tree over our surface up to some fixed depth. And instead of sampling from all of space, sample only from the nodes of the KD tree that might contain the implicit function. What this does is once you get over the initial cost of building the KD tree, it greatly accelerates your sampling procedure. I think here, if you want to sample 10 to the 6th points, it ends up being more than an order of magnitude faster to build this KD tree first and sample from it. And here, this is not an approximation. We're sampling from the exact same underlying distribution as if we did rejection sampling over all of space. We can also use this for mesh extraction, which is here we're talking about how to analyze these implicit surfaces, but sometimes you just want a mesh. And the usual way to get a mesh is to run marching cubes extraction or something like that over a voxelization of space over your implicit function. Again, we can just build this KD tree ahead of time. And for any KD tree nodes where the implicit function is strictly positive or strictly negative, we can skip processing them because we know we won't extract any surface geometry from those nodes. We run ordinary marching cubes, but only in the nodes of the KD tree that might contain the surface. And if you're doing this at low resolutions, it's not worth the trouble of building the KD tree. But if you're doing it at high resolutions, it again gives you an order of magnitude or more speed up to be able to skip all of the empty space. And again, it's exact. It gives you the exact same results as if you densely extracted from every node. We can also come back to one of the motivating problems I gave, which is suppose I'm doing robotic path planning or rigid body simulation or something, and I have 2 of these implicit surfaces, and I want to know whether or not they intersect and overlap each other. Well, here we can build a combined KD tree where each node is analyzed with respect to both implicit functions. And we say if the node is strictly outside of either shape, then we can discard and stop processing the node. Whereas if it might be inside either, then we subdivide and recurse. And doing this goes quite quickly. Eventually, our KD tree either gives us a certificate that there are no intersections between the 2 shapes, or we find some node of the KD tree where some point in that node is indeed in the intersection. Not sure what's going on in this example here. Maybe somebody showed up in the ER with a pair of scissors or something like that. And we had to do some implicit reconstruction analysis. One cool thing here is that this one actually runs in real time because building this KD tree is very quick, and we can quickly discard large regions of the shapes. And this was just kind of in my vanilla JAX implementation without any special tricks to make it run fast or anything like that. It already runs in tens of milliseconds per query. We can also do sort of the fanciest query that we looked at here, which is closest point operation. So this is to say, suppose you have some implicit surface, and for a point sitting in 3D space, you want to find the nearest point on the implicit level set. So here's an example again where I fitted an implicit network to a deer head or something here, and each black point is a randomly sampled point in space. And then the corresponding red point with the line connecting to it is the nearest point on the implicit level set. Doing closest point queries are kind of what KD trees were originally meant for. So we can just do a spatial search in our KD tree to find the nearest point on the level set to any particular query point. And you can actually do this two different ways. You can either, if you're going to do a lot of these queries, you can build your KD tree ahead of time and just traverse it. Or you can, maybe if you want to do just one of these queries, you could lazily build just the subregion of your KD tree that you need to answer the query, which would be a lot faster if you maybe only have one of these queries to do for a particular shape. We can also come back and show a quick proof of concept, which is this inverse rendering example I showed before, where you want to optimize the geometric content of a scene to match some target images. And here, this is just a really simple setup where I have synthetically rendered images with known camera parameters of a simple object. And here we're going to cast rays into the volume. And I think the loss here has two terms. One is a silhouette loss, and the other is just a photometric loss that matches the output of the shading function with analytically computed normals by sampling the derivatives of the network. And we just turn the crank on this loss function to make our implicit surface representation match the observed views. Now, if you work on differentiable renderers or inverse rendering or something like this, this is an extremely simple, naive setup. This is not a fancy inverse renderer. But the point here is that if you want to build up these kind of applications, having the ability to cast a ray into a randomly initialized neural network and find out where it hits the level set is really, really useful to implement things like neural renderers. And do tasks like inverse rendering. So hopefully having these kind of low-level geometric operations will enable inverse rendering folks to build up all kinds of new and exciting applications of this form by taking advantage of these low-level queries that are guaranteed to work even on randomly initialized networks. So the sort of high-level takeaways here on range analysis for geometric queries on neural implicit surfaces, we use this tool, which is affine arithmetic, on neural networks to bound the output of the network in space. And we didn't introduce a new network architecture or anything like that. We're just analyzing neural implicit MLPs or other architectures that you might already have. So doing this lets you build hierarchies and do lots of different geometric queries on your surfaces. It's slower than, say, the fastest SDF-based renderers or something like that. But the reason, what you're paying for here is that we give you a whole bunch of robustness and generality that enables different downstream applications. If you're interested in this, some directions still to push. Here, I mainly just did fairly simple MLP-based architectures, although there's a whole zoo of crazy neural implicit representation being used for these problems. So it'd be interesting to sort of push more into different architectures, or go even further downstream on building applications and objectives on top of these queries. And to kind of zoom way out here, in my opinion, the big picture here is that we have all of these representations for 3D data in computer vision and geometry. And all of a sudden, these neural implicit representations have sort of roared into the field and become extremely effective for all kinds of tasks. But something crazy is happening in that almost every paper, almost every research project presents a new, slightly different neural implicit representation. And on one hand, this is really exciting to have all of these new architectures showing up, each with new properties. But on the other hand, it kind of is a problem because we're not building one coherent set of tools that all work together. We're building a bunch of different tools that aren't necessarily compatible. So even though we started out in this world where we have this great sort of general purpose representation that's really easy to mix and match, we've started going in the other direction now by actually doing research on 200 different slight variants of this representation. So I think an interesting challenge and direction for kind of the next 5 years of neural fields implicit surface research is to say, rather than inventing lots of new representations, what are the ways to do more on one representation, or to impugn it to more properties, or to make these representations work together and sort of build a coherent set of tools that spans all of the different architectures and all of the different techniques we're using for these problems. And this is going to be what really sort of pushes this forward and lets neural implicit representations one day replace a lot of these old school triangle meshes and voxel grids and things like that. So I'm excited. I think a lot of the people here are doing a lot of the work that's getting us there. And yeah, I think the future is bright. So I'll wrap up there. The paper, there's code for this and lots of other work at my website there. And I think I'm having the opportunity to meet with some folks after this talk, but also if you're not on the schedule and you ever want to chat with me more, feel free to send me an email and I'm always happy to talk. So thanks a bunch.
Yeah, we have a few minutes before the hour. Folks have questions, feel free to ask them. James.
I have a question. Hi, Nick. Thank you very much for the very engaging talk, and the work's super great. So thanks. You mentioned at the end in the conclusion that, excuse me, we might want to use these kinds of techniques to build different differentiable renderers for solving inverse problems, right? And I work with natural images, and so oftentimes I don't really want to optimize an SDF because most of the scenes that I'm dealing with might not necessarily have nicely defined surfaces. So where do you think we might or we should investigate for applying these kinds of techniques to fluffier representations? Does that make sense?
Yeah, that's a great question. Yeah, so one thing is that you can already sort of do this, like the short-term answer is that you could already do this as is if you have, say, an occupancy function representation or something like that, or like a blurry density function, that if I told you, hey, we want to do rigid body simulation against your occupancy function that you found for your scene or something like that, what you would probably do is pick some level set of occupancy, use that to define the boundary of the surface, and then do rigid body simulation against that. This is not perfect. This is probably not the best simulation you could possibly do, but it's probably what you would do if you had to, get it working in a week. This machinery is all totally useful in that setting, right? You don't just have the whole point is it's not specific to SDFs. You can just run it to do these queries on some particular level set of interest of your occupancy function and start building up simulations like that. I think maybe the bigger picture question is yeah, like suppose though I don't want to work with like a hard surface representation that you get from this. So there what I'd say is that whatever queries or operations you want to use in that case would probably end up being something like volumetric integrals. You'd say something like where my things intersect, they become squishy, or I have some penalty that grows the more they intersect or something like that. And then the sort of terms you need to evaluate, maybe your like response functions or something, would be some like integral over space over the regions where the things intersect. And so now your queries or operations become robustly and accurately evaluating those integrals. And a bunch of the same numerical toolbox is extremely useful in that case. So we had one example I didn't show, which was just integrating like moments of inertia and masses and things like that over implicit representations. And here you just say, when I'm evaluating an integral, if I want it to have bounded error, then I need to know which regions of the function I need to recurse on and take more samples of to get bounded error on my integral. So doing this kind of bounded error evaluation ends up needing the exact same range analysis queries that I showed at the beginning. So you could use the same numerical toolbox to get out bounded error on integral evaluations, which would probably end up being the main operation you need to do these volumetric things too. So in that way, I'd hope at least that it could be a numerical toolbox for sort of fuzzy formulations in addition to just hard surface formulations.
Thanks very much.
Yeah, thank you. That was a good question.
Probably have time for one more question. Yeah, Srinath.
Nick, thanks a lot for the great talk. I think this is super inspiring work. To kind of follow up on James's question about modeling, I also work in computer vision, so we care about real things. Oftentimes, real objects, for instance, very thin objects like paper and clothing, cannot be modeled as an SDF, and also probably not as an occupancy, right? It depends on how fine scale you're looking at. Of course, every piece of clothing is probably at the microscopic level occupied by voxels and so on. What are your thoughts on unsigned distance fields as an alternative representation to these SDFs?
Yeah, this is a really good question. Yeah, even just the simplest case of open surfaces, right? Just saying I have a surface and it has boundary. This is already pushes you from, super simple, easy case to extremely hard, unknown, active research case. Unsigned distances are promising but hard, right? The great thing about level sets is that they always exist, right? Even if you randomly initialize a function, it still has a level set. It still means something. You can still operate on it. The hard thing about especially neural versions of unsigned distance functions is that if you randomly initialize it, what does it mean, right? You kind of have a regularizer and you can't interpret the function or do anything with it unless your regularizer is small and it's close to being an unsigned distance function. So I think there's been some really exciting work in this direction recently, but I'd still say it's kind of an unsolved problem to put these representations to work. And I guess maybe to take your question that you gave a little bit farther, right? You were talking about sort of making these things work for real world shapes. I love the grand challenge of just a tree, right? That has thin leaves, that has little twigs and stuff like that. I think the big challenge is that even if you do a really awesome reconstruction of a tree using some representation, and then you try to do, say, physics simulation against it, you still don't really want to do physics simulation against your reconstruction. You want to do physics simulation against the ground truth shape that you approximately have reconstructed. So I think that an important part of the answer to this is not just having more tools to simulate exactly against some representation. It's about building priors or something into your simulation step so that the answer is closer to the ground truth thing you attempted to reconstruct. And this is sort of the next frontier of these kinds of tasks.
Excellent. All right, well, we are at the end of the hour, so let's thank our visiting speaker one more time.
Thank you all so much, and thanks for all the great questions.